Hello and welcome back to Chapter 1, Section 5. Today we're going to look at analyzing graphs of functions. Before we get started, I want you to think about a graph as being a function that has a collection of ordered pairs, and your book is going to call those ordered pairs x, f of x, and if you remember, f of x is really your y, and it refers to when we plug this x here into our function for x, that's how we generate that y. So your graph is a function with a collection of these ordered pairs such that x is in the domain of f. And if you recall, the domain of f is set by your x values. So now that we've clarified that, let's go ahead and look at example 1. It says use the graph of f of x equals 3 minus x squared to find a, the domain, and b, the range. Now you can pull out your graphing calculator, that's fine, but real quick, let's just look at our function. I see I have a quadratic function that has a negative value in front, so I should automatically start thinking that I should have some type of a parabola, and because of that negative sign, I should know that my parabola is going to be facing downward. Okay, so if I sketch this graph, and I'm just going to come here and draw in a set of axis points. Something that looks like that. And I'm going to make each tick mark a unit of 1, so there's 2, 4, and 6. Here I have 2, 4, and 6, and those are all negative. 2, 4, and 6, and a negative 2, negative 4, negative 6. Okay, so now when I graph, because of this 3 right here, that's my y-intercept. So I'm going to plot that there. And if I set this equal to 0, I know that x is going to be plus or minus the square root of 3, which falls somewhere in between plus or minus like 1, I think it's like 1.7. So we end up with a graph that looks something like this. Now to look at our domain, or part A. Okay, remember, if you think about the domain, or I like to think about the domain as the x values, and instead of thinking about what x can be, I would rather look at it and say what can x not be, and then everything else will be all real numbers. So if I look at this function, I know x can be negative numbers, I can include 0, and I can also include positive numbers. So that tells me then that my domain is all real numbers. Likewise, when I go to look at my range, I see that my range, or my y values, are going to be anything in the negative region, so anything down here, and it looks like I have some in the positive region too, up until I hit that point of 3. So my range then is going to be all real numbers less than 3. And I've just concluded example 1. Before we move on, let's think back to section 1.4, which dealt with functions. I want you to remember that the definition of a function requires that for every input, there's exactly one output. And this means that for every x value that you get, there can only be one y value with that corresponding x value. Now you can go ahead and look at charts, you can look at graphs, or you can use what we call the vertical line test, which from this point forward is going to be referred to as the VLT. And what the vertical line test says is that if you have a set of points in a coordinate plane, and if no vertical line intersects the graph at more than one point, then we have a function. If a vertical line will hit your graph twice or more times, then you failed the vertical line test, and it tells us that we do not have a function. So this is going to lead us to example 2, where we're going to use the vertical line test to decide whether the function y equals a negative 1/4 x squared represents y as a function of x. So again, I've made my axis. I've now gone in and plotted out some points, and we'll see that we get something that looks like this. And again, you should have known that you were at least going to have an upside down parabola because of the negative and then the x squared function. So now, to use my vertical line test, I'm going to go ahead and draw some vertical lines. Now what I'm noticing is it doesn't matter where I draw my vertical lines, at most I'm only hitting my function at one point. So because I'm only hitting it at one point, this tells me that y is a function of x. And that makes me happy. Now you don't have to write this down, but let's just think of a function real quick that might fail the vertical line test. If we sketch something that looks like this, and I know that if I have a square root function, so we'll just say f of x equals plus or minus, we'll say the square root of x. Now, if you recall, a square root function is going to look something like this. Okay, this is going to represent the positive side of your square root. This is going to represent the negative side of the square root. Now if I go in and I do the vertical line test, I hit my my graph at 2 places. So because I've hit this function at more than one point, in this case y, or f of x, so I could actually put y here, is not a function of x because my it fails a vertical line test essentially, which tells me that for every input I have more than one output. In this section we're going to also look at zeros of a function. The zeros of a function are the x values for which f of x equals 0. Now you may also encounter, or another word for zeros would be a solution, x-intercepts, or roots. These all have the same meaning. We will now look at how to find the zeros of the function in example 3. So we're going to look at this function, f of x equals 2x squared plus 13x minus 24. Now you can go ahead and try to factor this if you like, or you can use the quadratic formula. And if you remember, the quadratic formula is x equals the opposite of b plus or minus the square root of b squared minus 4ac divided by 2a, and the coefficient on x squared will be our a value, the coefficient on x is b, and our constant is c. So if we go ahead and plug into that, we end up with the opposite of b, which is a negative 13, plus or minus the square root of 13 squared, which is 169, minus 4 times a, which is 2, and c, which is a negative 24. And I'm going to divide all of that by 2 times a, which was 2. So when we simplify, that's a negative 13 plus or minus the square root of 169. Let's see, this negative 4 and negative 24 become positive, so I really have 169 plus 4 times 2 is 8, 8 times 24, and I get 361, and we're going to divide that by 4. When you simplify this, you get x equals 3/2 and a negative 8. The square root of 361, this here is really 19. So when we go negative 13 plus 19, divide that by 4, you get 6/4, which reduces down to the 3/2. Or if I go negative 13 minus 19, divide that by 4, you get a negative 8. So these right here would be the zeros of your function. Now if you did go ahead and factor, your factors would have been 2x minus 3 times x plus 8. And from your factors you could have set each factor equal to 0 and you still would have gotten the 3/2 and negative 8. The next thing we're going to look at are increasing and decreasing functions. Now this is a very critical topic for those of you that go on to take calculus. Okay, when we are looking at increasing functions, and increasing functions means that we have a positive slope or a positive rate of change. And a positive slope is going to look something like this. It's rising as you go from left to right. A negative slope or a decreasing function is going to look something like this. It's going down or decreasing as you go from left to right. And a constant rate of change or a constant function means that there's really no change at all, and that's just shown by a horizontal line, something like this here. For example 4, we want to use the graph of f of x equals x cubed plus 3x squared minus 1 to describe the increasing and decreasing behavior of each function. So let's go ahead and graph this. I would recommend that you actually graph this on your calculator if you have one handy as well. Okay, but anyways, this is kind of what your graph is going to look like. We have a couple key coordinate points at -3, -1. I have -2, 3, 0, -1, and 1, 3. Okay, these are just a couple key points that I pulled off. Okay, now our example wants us to describe the increasing and decreasing behavior. So let's start out by looking at our increasing behavior. I see that I have a function that has a positive slope or rate of change, and it looks like it's positive from here all the way up until I hit this point. So, to show that, I'm going to use a parenthesis, okay, which means that I technically do not include this, okay, and I'm coming in right here, I'm coming in from the negative infinity because this graph is going to continue to go on in this direction. So I'm going to write a negative infinity, and I'm only looking at my x values too, so you know where I'm getting these. And then my x value as I get up to here is a -2. And I'm also going to include a parenthesis right there. If I use a bracket, and a bracket meaning something that's squared off, okay, that means to include that point. But in this case, I'm not including the point -2 because at -2 something's changing. It's changing from positive to negative. And you'll get into those topics when you get into calculus. Okay, then it looks like my function is going to decrease, so I don't want to include that one right now. But then I hit another point where I'm starting to increase. And that's this little piece here. So I'm increasing beginning at x equals 0. So again, I'm going to include 0. And my function then just continues to go on in this direction, which means I'm going to approach infinity. So I'm going to include infinity. And I have no other pieces of my graph that are increasing, so that's all I'm going to include right there. Now I'm going to look at the decreasing behavior. And I see that I'm decreasing from x equals -2 all the way down to x equals 0, or in this region. So my decreasing region is going to be shown from -2, which again I'm going to use the parentheses, all the way to 0. And I'm going to close that with another parenthesis. So this means my function is increasing again from negative infinity to a -2, which is this piece, and from 0 to infinity, which is right here, and I'm decreasing from -2 to 0, which is in this region. The next important topic that we're going to look at deals with relative minimum and relative maximums. This again is another critical calculus piece for those of you that move on. Now relative minimums and relative maximums come from points at which a function changes from increasing, decreasing, or constant behavior. Kind of like on the last graph where we had something that went from increasing to decreasing, that would be a relative maximum. And if we had something that's going from decreasing to increasing, that would be a relative minimum. So let's just look at a function. If I have something that looks like this, Okay, and this is just some arbitrary function. This right here would be a relative min. And this right here would also be a relative min. Okay, and the thing with relative minimums and maximums is you can have more than one. Now this here is a peak, so this would be a relative maximum, just like this peak would be here. Even though this peak is higher than this peak, okay, they're both relative maximum points because it's essentially where our function is going from increasing to decreasing. I'm increasing to decreasing here, and my minimums are found when I go from a decreasing to increasing, just like I did here. I will show you on your calculators, okay, and I know how to do this on the 84s. If you have something else, we'll have to kind of work our way through it, but I will show you how to do this on your calculators. You can actually find the exact points, max and mins. Example 5 says to approximate the relative maximum of negative 4x squared minus 7x plus 3. So I'm going to go ahead and start by graphing my function. Okay, again, please graph this on your calculator for a little bit nicer graph, but you get the gist of what we're looking at here. Now, what we're looking for is the relative maximum point, okay, which occurs right here, because a relative max comes from when my function is increasing and then we change to where the function is decreasing. So I'm looking to find that relative max here. And again, I'll show you how to do this on your calculator, but when I do this, I found this point here to be a negative 0.875 for my x, and my y is about 6.063. If you have questions on this, please let me know. And the last thing we're going to look at today deals with the average rate of change. Now, you may not know this, but the slope of a line is really considered a rate of change because it's changing at something like miles per hour or minutes per second or foot per second. I don't know. It's a rate. That's what the slope is. So a nonlinear graph whose slope changes at each point is called the average rate of change between 2 points. Okay, and when we look at the average rate of change between these 2 points of a line that's going through the 2 points, this is actually called our secant. So I know it's been a while since some of us have had geometry, but if you have a function that looks like this, and you go in and you have a point here and a point here, and you connect those 2 points, okay, this line here is your secant line because it's going through the 2 points on that graph. So we're going to look at the slope of a secant line, and we're going to designate that by m with the subscript of SEC for secant. We are going to calculate the slope of a secant line just like we've calculated all of the other slopes. It should actually be a change in x, or I'm sorry, change in y. So please change this to y divided by a change in x. Okay, and if you remember, f of x is really a y value. So this is like your y2 minus y1, or your f of x2 minus f of x1, divided by x2 minus x1. It's, again, your slope formula. So example 6 says to find the average rate of change of the function f of x equals x squared minus 2x from x1 equals negative 1 and x of 2 equals 3. So the first thing we have to do is we have to find out what f of negative 1 equals and f of 3 equals. So if I plug a negative 1 in here, negative 1 squared is 1 minus 2 times a negative 1. Well, negative 2 times a negative 1 is going to become a positive 1. So I have 1 plus 1, which is going to give me 3. So I have the coordinate point negative 1, 3. And f of 3, this is going to give me 3 squared, or 9, minus 2 times 3, which is 6. 9 minus 6 is 3. So then I have the coordinate point 3, 3. So when I go to calculate the average rate of change, I'm going to use my slope formula. So I end up with 3 minus 3 divided by 3 minus a negative 1, which really becomes plus 1, or I get 0 divided by 4, which is really 0. So a slope of 0, remember, is a horizontal line, which tells me that there is no change. Now we're going to do the same thing for part B, except part B wants us to evaluate the function when f of x is equal to 0 and f of x2, which is going to be f of 1. So when I plug a 0 in, we're going to end up with 0. If we plug a positive 1 in, we're going to end up with 1 minus 2, which is a negative 1. So these coordinate points then are going to be 0, 0, and 1, negative 1. So when we go to calculate the slope, we end up with 0 minus a negative 1, which really becomes a positive 1, divided by 0 minus 1, or I end up with 1 divided by negative 1, which is negative 1. So your average rate of change is a negative 1 then. And our last example for the day is actually a good calc problem, and it says the distance s in feet of a moving car from a stoplight is given by the function s of t equals 30 times t to the 3/4. We want to find the average speed of the car from t1 equals 0 to t2 equals 5 seconds. So the first thing we have to do is we have to evaluate our function s of 0. Okay, if I plug 0 in for t, that's going to give me 0. So this coordinate point is 0, 0. And we have to look at s of 5. And when I plug 5 in for t, I end up with 100.31. So I end up with a point 5 and 100.31. So now I'm going to take these two coordinate points that I just calculated and plug them into my slope formula to find the average rate of change, or the average speed. So I have 100.31 minus 0 divided by 5 minus 0, and this equals 20.06. And because it tells me that my distance is in feet, my time is in seconds, I know that this is feet per second then as an average rate of change. And today's fun fact is another cartoon. I hope you guys have a great day, and we will see you tomorrow.